Hello and welcome to our OPTI 380A final project, active mode locking of a helium neon laser. I'm Race.
I'm Lucas.
And here's our gracious champions, Kyle, Randall, and Cody. Let's get into it. Mode locking is an essential part of research and in many fields of industry. Our demo demonstrates the concepts and basic alignment to achieve this phenomenon. Mode locking takes a continuous wave output and converts it to a pulsed output. This is used in areas such as ultrafast spectroscopy, punt probe experiments, medical imaging, and optical communication. Some research groups here at the College of Optical Sciences that use these techniques include, but are not limited to, the Seiler Lab, Jones Research Group, Ultrafast Fiber Lasers and Nonlinear Optics Group, and many others.
Mode locking is the method of creating pulses from a continuous wave output by modulating the CW output back into the cavity to meet specific criteria that we will get into. Our experimental setup involves two coupled resonator cavities, a HeNe in an external cavity from a mirror M3, an acousto-optic modulator AOM, which diffracts the beam into the main output and the secondary cavity output. The main output will be used to verify that we have successfully mode locked our laser. Resonator cavities have an allowed range of frequencies or wavelengths called modes, and the spacing between these modes is the free spectral range, or FSR, and is given by C over 2L, where L is the length of the cavity and C is the speed of light. The laser medium only allows a certain amount of modes to exist in the cavity, creating a narrow spectrum.
The AOM uses a radio frequency driver to oscillate the atoms of a crystal, which produces the diffraction needed to split the beam. The driving frequency introduces a phase shift in the first diffracted mode, which will be sent back by M3 into the AOM, doubling the phase shift and then injected into the cavity, thus meeting a criterion of mode locking. To reduce mode variation due to environmental fluctuations, the injected beam should be phase shifted by 1 FSR to overlap with the existing modes in the cavity, thus meeting another criterion of mode locking. When this condition is met, the existing mode variations are minimized and we're left with perfectly in-phase modes. These modes are now locked and will interfere and produce pulses.
Here's our setup. It consists of our long cavity HeNe laser, the AOM, a routing mirror, our external cavity mirror M3, as well as another mirror to route the main output beam through a beam splitter. This will be measured on a scanning Fabry-Perot interferometer and a fast silicon photodiode. It will further be characterized on an electrical spectrum analyzer, oscilloscope, and fast scope. When all criteria are met, the electrical spectrum analyzer will display the interference frequencies converging to the FSR frequency when we adjust the AOM phase shift. The oscilloscope will show the mode fluctuations disappear and lock down to be in phase with each other. The fast scope will show the actual pulse duration and shape. In conclusion, we were able to achieve clearly visible pulses that lasted approximately 6 nanoseconds. The pulse duration is governed by the gain bandwidth of the HeNe laser and is not a tunable parameter. The pulse shape is not as Gaussian as we would expect, but changing the position of M3 for the length of the external cavity will provide varying pulse shapes. The ESA frequencies converge to a very well-defined peak. The FPI modes on the oscilloscope clearly locked down, showing the phase matching condition, and all variation was uniform across the spectrum.
Some areas that have room for improvement are the AOM driver, mirrors, and the HeNe itself. Using an AOM driver with a finer resolution of frequency modulation simplifies meeting phase matching criteria. Alongside that, a better amplitude from the driver will give you more power in the diffracted injection beam to make pulses stronger. Cleaner mirrors will allow for less loss in the beams, and a better mount for the HeNe itself, with temperature control as well, will allow for more stable pulses over longer periods of time.
Thank you for listening, and once again we'd like to thank our faculty and graduate champions for their time and assistance. Have a splendid day.